Welcome back. Let's take a look at average values in statistics. Okay, imagine for a moment that we're playing the following game. So let's say that you flip a coin, and that if you get heads, I'll give you $1, and if you get tails, I'll give you nothing. You could imagine playing this game many times and asking the question, on average, how much money are you going to get each time you play? Well, we can go and calculate this, and you might have an intuitive sense of how. So average payout. Right? So it's going to be the $1 payout times the probability of getting that payout, so which is a half, plus the other possibility, a payout of 0, times the probability of getting that payout. So let me label this. So payout, so payout times the probability of that payout, and notice that we're summing over all possible outcomes here. Now, in this case, the arithmetic is straightforward, and if you do the math, you'll find that the average payout here is 50 cents, which probably jives with what you might expect. Now, there's one interesting feature of this, right? Notice that the average payout here is not an actual amount you could get, right? You either get $1 or you get nothing. The average payout just represents what you might get on average when you do this many times, not something that could actually happen. So this lets us generalize the concept of an average value, and sort of armed with intuition from this example, we can write down a general definition. The average value of some quantity and I'm going to use the brackets here of a random quantity is given by n, average value of n equals the sum over all possible values. So I'll write that as a summation over n. It's a summation of n times the probability of getting that value for n. So this is just a generalization of what we did here. We take the random value, multiply by the probability of getting that value, and sum over all the possible values that that random quantity could take. So now, let's have you think about an example involving rolling a die. Okay, So let's now think about the average value that you might roll when rolling a fair six-sided die. So the average value n, according to our definition, is going to be the value times the probability of that value summed over all possible values. So that's going to be 1 times the probability of rolling a 1, which is 1/6, plus 2 times the probability of rolling a 2, which is also 1/6, etc. So I'll just fill that in for you. Plus 3 times 1/6 plus 4 times 1/6 plus 5 plus 6 times 1/6. We have, in this case, the same probability for all my values because we're assuming a fair die here. And if I factor out, we have 1/6 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6. And if I do the arithmetic here, this is 1/6 times 21. And this simplifies to 7. Let's see, I can cancel out the 3 here, so I have a 2 and a 7 upstairs. So we get the average value that you might get when rolling a die, 7/2 or 3.5. Again, notice that the average value is not a value you could actually get, just like we saw with the coin flipping money game example earlier. So naturally, one might ask, what does this all have to do with quantum mechanics? You might be able to ask a similar question in the following way. If I have a particle, and it's described by a wave function, and I measure that particle's position, aka I try to detect where the particle is, what's the average value of the position that I would get? So for a particle that's described by some wave function, and I'll just write psi of x here because we're not going to pay attention to the time dependence for now. What is okay, well, we just have to generalize the concept with the discrete case that we had just talked about. So, well, first though, let's think about what this average value physically represents. So, x, the average value of x, or in quantum language, we call it the expectation value of x. Right? So, is the average value you would get if you measure the position in many identical systems. Of my particle in identically so imagine we had sort of the same situation duplicated where we had many particles all described by the same wave function, that then if we took that collection and measured the position of our particle, the expectation value, and let me label that, is the average value you would get. Expectation value. Now what it is not, and we'll say more about this later on because it turns out that measurement in quantum mechanics is really, really weird. So it's not what you get if you measure the same system repeatedly. The average same particle so as we'll talk about later on, measuring something in quantum mechanics changes it in a really important way. So there's no measurement in quantum physics that doesn't disturb the system. Okay, so having talked about what the expectation of value of x means, how can we go and calculate it? Well, we can just apply the idea we talked about earlier. So mathematically, the expectation value of x is given by, again, there's a summation involved. It's going to involve a summation, this time an integral, since x is a continuous random variable. It's going to be the integral from minus infinity to infinity of the value of x, so it's going to be x, times the probability of getting that value, which is going to come now from our probability density. So that's going to be psi of x modulus squared dx. So it's the same thing as we saw before, those same three elements. We have the value. Our probability density here is thus probability. Our psi modulus squared dx is a probability of that value. And then the integral means that we're summing over all possible values. Sum